All right, good evening, everybody. So we're going to tackle the last problem in our final exam preview. It's going to be number 10 here. If you watch them in order, you're not going to get the order I put them in. Okay, we're going to construct a power series for the function f of x equals x over 4 plus x squared. This is a hint. Make a power series for this one and then multiply by x. Okay. So determine the interval of convergence. So here's what we're going to do. Oops, I need that back. This is x over 4 plus x squared. All right. So what we're looking at here is we have x over 4 plus x squared. Now, where does this come from? Here. Remember this. Remember, if I have 1 over 1 minus x, and I know that negative 1x, that x lives in that region, right? Can I make a power series out of this? And that is, of course, the answer is going to be yes, because you remember, right, that's r to the n, right, as we sum. If r is, right, absolute value of r is less than 1, that this geometric series converged, didn't it? And what did it converge to? It converged to 1 over, well, converged to a, right, over 1 minus r. That looks awfully familiar, doesn't it? Right? If a is 1, that we're going to be able to do that. Now we're going to use this to deal with other functions that look like fractions like this. Okay. So here's what we're going to do with that. So we're going to say, well, right now it says hold the x off. Okay, so we're gonna push the x. We're going to pull the x off to the side here. Okay, so there's going to be x times 1 over 4 plus x squared. Now it doesn't quite look like this yet, but what if I factor a 4 out of this thing, right? What if I say this is 1 over 4 times 1 over 1 plus x squared over 4. Okay, so if I push it back in, what happens? I get the same thing. Okay, so there's an x here. So what I'm going to do is I'm going to say, well, this is 1/4. Okay, that's my a, by the way. And then we have 1 over 1 plus, can I do this? Can I say x over 2 squared? Okay. So there we go with that. All right. So the next thing we're going to say is, wait a minute, now this thing has a minus in it, and yours doesn't have a minus in it, but it does. So this is x times 1/4, okay, times 1 over, and this is 1 minus negative x over 2 squared. You see how that happens? Okay. Now take a look at that, right? We decided that this was my r, right? This is a 1 minus r. Could we do that again? Right? Could we say that this is x times, I'll put the 1/4 here, it doesn't really matter, because that's going to be my a. And then we're going to have sum, right, of, well, of r, well, actually not r. What do we want? We want to the x over 2, right? We want x over 2 squared, right? I think there's a negative in here. Negative. Okay. Raised to the n as n goes from 0 to it marches on. All right. So if you came across and saw this, right, as a geometric series, right, we have 1/4. Okay, times, and here I have negative 1 to the n of x over 2. Actually, no. Yeah, we need that x. We need the negative here. Well, I'll put it inside. It doesn't really matter, but we're going to go ahead and do it this way. We're going to say, well, here's my negative. Okay, x over n squared. Boom, raised to the n. Okay, so this whole thing in here, right? That's my r. R happens to be negative, that's fine. Here's my A, and then we're just going to march this thing out. And then here's my X over here. Okay. So that's what we're going to do. All right. Now, let's see here. Let's look at a couple of these terms. I just want to, I don't want to leave you with like, here, it's magic, it happens. Okay. So what we might want to do here is kind of mess around with this a little bit and see if we can't work on something here. Let me see if I can set this up for us, and I'll be right back. All right, there we go. So we were working on the fact that we had a geometric series, okay? And let's just go ahead and take a look at what's going to happen here. So this is going to be, all right, this is going to be x over 4. We have a sum, right? N equals 0 to forever. Okay, we've got a negative. I'm going to go ahead and move the negative 1 out. I just don't want the to deal with it. We have an x squared over 4, and this is raised to the nth power because that's what we're doing our geometric series on. Okay, so let's simplify this a little bit. Okay, and here we have x over 4, negative 1 to the n, and here we're going to have x to the 2n over x to the over 4 to the n. Okay, and then the last thing we're going to do is we're going to put this x, we're going to include this x in here. So we have sum negative 1 to the n, okay, and then we have x to the 2n plus 1 over 4n plus 1, right? And that is our series solution, right? That is our power series for that function. Now I want to do something like compare the two of them. Okay, so here we go. We have x over this was 4 plus x squared. So let's just take a look at what that looks like. Okay, so we have fx equals x over 4 plus x squared. Okay, so go ahead and zoom in on this. Actually, let's see here. What can I do with this? First off, let's make you bolder. Okay, and thickness, let's go 3. Okay. All right. I don't know if that helps, but there we are. Okay, we're gonna close in on here. I'm gonna go ahead. I'm also gonna give it a range. Okay, so we're gonna do negative 2 x up to 2. Okay, so that cuts it off. Okay, that's how you do that, by the way, if you're dealing with this. Okay, but I'd really like to kind of zoom in real close here. And let's compare it. Okay, let's compare it to what our series looks like. All right, so here's our series solution. Let's take a look. If n is equal to 1. Okay, if n is equal to 1, well, actually n is equal to 0, right? 0, 0 here. We just get x over 4. Okay. When n is equal to 2, or n is equal to 1 rather, sorry, we get negative, right? There's negative. We have x squared plus 1, right? So x to the 2 plus 1, that's x to the 3 over n is equal to 1. We have 4 squared under here. What is 4 squared? It's 16. Okay. N is equal to 2. Okay, so we have 1, so it's positive. Okay. 2 to the, right, that's 2 times 2 is 4. 4 plus 1 is 5. And then squared 4 to the cubed is going to be 64. Plus, actually, it's going to be minus. Okay. So I just wanted to add up a couple of these so you can kind of see what's going on with this. All right. So so here we are. We have x over 4. So we might do, say, y1 equals x over 4. Okay, and let's go ahead and change that to something much later and something much later, and maybe not all the way through. Okay, so you can see that's, if you only needed a small amount here, if you were very close to 0, you could approximate this function by x over 4 and probably do pretty well. Okay, if you were between a half and negative a half, that would be okay. Okay, what if I do y2 is equal to x over 4, what was the next one? It was minus x cubed over, I think it was 16, wasn't it? Okay, and again, we'll do the same thing here. We'll go ahead and change that. We'll go ahead and change this to a 0.5. Okay, and let's change this color to a green. Okay, so you can, it's light, it's fainter. Okay, let me get rid of, that may have been too much to do. Okay, let's go with 0.7. Okay, so you can see, right, the green line approximates this curve a little bit better for a little bit longer. Okay, so again, maybe if you were between 1 and -1, that this wouldn't be a bad thing. And when it comes down to like figuring out slopes or integration, actually this integral is not too bad. But take the derivative, like, gotta use a quotient rule. Yeah, no thanks. Take the derivative here. Oh, easy, right? Calc 1 student can do this, no problem. Okay, and then y3, right, we have x over 4, okay, minus x cubed over 16, okay, oops, come back up here, plus, and what was it, it's x to the 5th over 64, I believe, right? All right, and let's go ahead and make this a little bit lighter. Okay, so we'll do 0.8, and again, we'll make it little dotted lines here, and I'm going to go ahead and scratch out these guys because there's a lot on the table now. Okay, but you can see like the blue line, right? The blue line approximates the green line, or approximates the black line even a little bit better, right, as it goes forward. And you're going to keep doing that, right? The more terms you add, the more accurate you're going to get for this thing until you've gotten the whole thing. Okay, so that's not so bad. This this actually was the job of mathematicians for a very long time because we didn't have calculators out in the field. This is before I was, before I worked, so this is not me. But we didn't have calculators out in the field, and engineers would have to either deal with this function, right? Or they'd have to deal with, this one, right? Because we probably stop at about here. And we did. We sent men to the moon with this technology. Okay, so doing these series things, this actually is a really effective way to go. And it's one of those things you should always hold this in your back pocket. It's like series solutions. They're just a little magical. And I'll tell you that I remember we were working on a satellite problem where we were trying to figure out, right? We were trying to measure it. We had the satellite here and then here, and we were trying to figure. Actually, we were going straight above, so we had it here and here, and there's like a little satellite here. Okay, little Viking ship in the sky. We're trying to figure out the length, okay, based off of these two beams. And you can imagine, right? We do the triangle thing. We have a square root in here. We have hypotenuse, and we're, but the distances were so large. Okay, we had, it was up, I think, 6,000 kilometers. Anyway, and satellites are measured in meters, so that's the order of magnitude. And they kept subtracting the different pieces, and it's like we kept getting 0. Okay, this line and this line were the same for the limits of the computer. So what we did was we had to get this one, this line here, and we were stuck in a meeting because I don't know what to do. And our senior scientist said, "Hey, can you approximate that with a series?" I'm like, Bill, that's brilliant. What do you suggest? He's like, No, you're the mathematician. You work it out. I came up with a brilliant idea. I'm the physicist. Damn it, Bill. But honestly, that was one of the better days I ever had at work, so I'm not going to complain, right? But pulling that, hey, could you approximate that with a series? Always that move to make you seem like you're the smartest person in the room. Okay, but that's how you do that. That's what I'm looking for an answer. Okay, and the reasoning behind how you set it up. Okay, so I'm going to go ahead and let you go with that, and I think that does it for a final exam. I'll probably pick a slightly easier problem again. On the final that I gave, this one, between this one and this 12B, these were the two hardest problems on the test. Okay, so I know I need to tone these down a little bit. If I just toned this down to a 1, it would have been easier, right? So, oh, we need radius of convergence. Sorry. Okay, I kept talking. Radius of convergence. So in order for this, right, in order for this to work, this x over 2 squared, this has to be less than 1. Okay, so x over 2, right, squared has to be less than 1, has to be greater than negative 1. Okay, let me not put those in just yet. If I square both sides, or if I take the square root of both sides, right, we just get x has to be less than 1. Absolute value of x has to be less than 1. Okay. So we're going to have x has to be between 2 and negative 2. Okay, that's absolute value stuff. So that's how we're going to do that. But you still have to test your endpoints. Okay, so I'm going to go ahead and test x equals negative 2. All right, let's go back to my original series. Right, we had an x over 4. Right, we had a negative 1 to the n, and we had an x squared over 4 raised to the n. Plug in negative 2. So we have negative 2 over 4. Actually, we have 2 over 4. I'll put the negative outside. That's what I did. Okay, so we have a half. We have 1/2. We have negative 1 to the n. If I plug in a half here, or if I plug in 2 here, right, or negative 2 or positive 2, so negative 2 or positive 2, we end up with, right, we end up with 4 over 4. So we end up with a 1. So what happens here? We just get half for x equals 0, minus a half, plus a half, minus a half, plus a half, dot, 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 dot. Even though I know this toggles, it goes back and forth, it doesn't converge. So you can't have this equal to negative 2. It has to be smaller. It has to be a little bit bigger than negative 2. And it has to be a little bit smaller than actual 2. So my radius of convergence here is x has to be between 2 and negative 2, strictly. Okay, and that's how you do that. All right, now I'll sign off.